Welcome to another video from Roland Mösel, founder of planetary engineering group Earth. This time it's about 3 new patents about more efficiency at cooling, heating and domestic hot water creation with heat pumps. To understand better the heat pump, we start first with the water pump. The water pump uses power to pump water in a direction where it would not naturally flow. Naturally flows water from up to down, but not from down to up. We can reverse this, and when we do this, we have a hydropower plant. The water comes from up down, and we can generate electric power with this. And now the heat pump. The heat pump uses mechanical power to make a bigger temperature difference between two sides. Normally, heat mixes together and we have on both sides after some time the same temperature, but the heat pump increases this temperature difference. For example, we take on the left side 3 kilowatt heat out. We use 1 kilowatt electricity and we had on the hot side 4 kilowatt more heat. You see, what we take out from the cold side and the mechanical power we use adds up to the warm side of the heat pump. Here we have the formula for the water pump. Meters height difference, how many kilogram of liquid we pump, then multiply with 9.81 meter second to the square for Earth's gravity, then divide by the efficiency, and you know exactly how many joules you have to use to pump this amount of liquid up. We have also a formula for the heat pump and also for all engines which use heat to generate power. This formula was discovered 2 centuries ago by Sadi Carnot. At the left side, it's at steam engines, internal combustion engines, and the Stirling engine. And on the right side, power for heat transport. We have it at the heat pump, the air conditioner, the refrigerator. These are all heat pumps, but we name it by the most usual application. Here we have the formula of it. For example, on the left side, heat to power, we have an engine which has 700 degrees Celsius on the hot side, and at the exhaust, the cold side, it's 200 degrees Celsius. And with the formula, we can determine that the maximum of theoretical possible efficiency is 48.6%. On the right side, we have an example for power for heat transport. Here we have 7 degrees Celsius on the cold side and 35 degrees Celsius on the hot side. And we use the same formula and we get an efficiency of 0.091, and now we make the inverse value of it. It's 11, and 11 is in this case the maximum possible coefficient of power. This means I put 1 kilowatt mechanical power into the system and I get 11 kilowatt heat out of the system. Normally heat pumps have about 40 to 45% of this theoretical possible maximum coefficients of performance. When I have a heat to power process, a large temperature difference is good for more efficiency. the higher the temperature difference between hot and cold side of the process, the better efficiency I have. At the power for heat transport, exactly the opposite is true. I want a very small temperature difference between hot and cold side for a high COP coefficient of power. Here we make an example with a house and we have two different heat pumps. One air heat pump and one water heat pump where the power comes from an underground collector in the garden. We start with 2 degrees Celsius air temperature and the ground collector has the same temperature. We want 20 degrees Celsius room temperature and the floor heating has 35 degrees Celsius flow temperature and the heat demand of the house is 5 kilowatt. At this, both heat pumps have the same COP, 3.74, and use natural also the same amount of power, 1339 watts. But now it becomes very cold, minus 16 degrees Celsius. And so the heat demand of the house doubles from 5 kilowatt to 10 kilowatt. And the ground water heat pump has the same coefficient of power, 3.74, because the underground collector has still 2 degrees plus and uses now 2678 watts to produce the 10 kilowatt heat demand of the house. But the COP of the air heat pump drops dramatically to 2.42 and would now use 4138 watts. But this is only the half truth, because most times the heat pump is not big enough dimensioned. Yes, they say 10 kilowatt heat output is no problem, yes, at 2 degrees air temperature, but now we have minus 16 degree air temperature. And here the COP drops to 2.42. And when we have only a 3 kilowatt compressor in the heat pump, the heat output will be only 7,250 watts. Oh, but the heat demand of the house is 10,000 watts. What to do? Oh, no problem. We take an electric heater. We take 2,750 watt electric heating and we have 10,000 watt thermal power and the heat demand of the house is okay now, but we have a dramatic increase of electric power demand. This we call the degeneration of an air heat pump to an electric heater. I have a German study about the usage of air heat pumps in Austria. There's always a big question if everybody did it. Oh, let's assume a small settlement of 100 houses. And everybody has such an air heat pump. And such settlements are usually equipped with a 400 kilovolt ampere trafo station to the middle voltage grid. But this would be in this case much too small. They would have to change this trafo station to 1000 kilovolt ampere. And what would be if all 1 million of such air heat pumps would be in Austria? Oh, the grid would break down. The salesman of an air heat pump tells you, oh, look, the air heat pump is 7,000 euro more cheap than when you would make an earth collector or a deep drilling. And how do you want to make this 7,000 euros? Maybe you use with the air heat pump 100, 200 euro more for 1 year. It's not efficient to do it. He puts all the load to the society, because the society would have to increase for very cold days all the power grid only for these air heat pumps. So we look for the first patent. We make a big low temperature storage, very big. Even at the small German next generation house standard size, 40 cubic meters. And we have an air heat pump or more than one air heat pump. And the task of the air heat pump is only to fill this low temperature heat storage up to maybe 19 degrees in usual cases. And at the low temperature heat storage, we have a water-to-water heat pump for floor heating, for domestic hot water, and also we can use direct the heat of the low temperature heat storage, direct with a plate heat exchanger for other applications which need only low temperature. And where to put this low temperature storage? Best place is between the ground of the house and the bottom of the house. Here in blue color we have this low temperature storage. We have only 8 centimeters of thermal insulation towards the ground and up only 8 centimeters of thermal insulation, because maybe the low temperature heat storage has 15 degrees and above we have 25. We have a very small temperature difference here. Here we have typical temperatures. Flow temperature for floor heating in an old building, 35 to 40 degrees. At a low energy house, 30 to 35 degrees. Then we have the flow temperature for wall and floor heating in the Germany next generation house. Because we have double the space of the heating system, walls and floor, we have only a very small temperature difference and we can use a very low flow temperature. And then we have flow temperatures for floor heating of driveway, of sidewalks, of garage, and keep the glass house frost-free. These are new applications, not typical for normal houses, but I think floor heating in the garage, that the garage has maybe 10 or 12 degrees Celsius, is very useful when you park an electric car in it, and it will even save energy. How much? We have to determine by real-world experiment. And now we have on the right side the temperature ranges from the low temperature heat storage. In the middle, a little bit down, it's 7 Celsius between 12 degrees and 19 degrees, and even this is 325 kilowatt hours of heat. When the weather forecast says, oh, very extreme cold weather ahead, we could theoretically go up to 40 degrees Celsius, and this would be 974 kilowatt hours of heat. And in an emergency, oh, very cold days, much longer than we thought, we could go down to 5 degrees, and these are another 325 kilowatt hours of heat. Normally, a heat pump works all the day round. Oh, the air heat pump works 5 o'clock in the morning, it's very cold, and the heat pump works. Oh, very inefficient method. We have in winter in Middle Europe usually a 10-degree difference between the coldest hour of the day and the warmest hour of the day. And this we use here. Here, on a normal winter day, we use the air heat pump only on the hottest hours of the day. And all the other time we don't use it because the efficiency goes down because it's very cold outside. And what happens when the weather forecast tells, oh, very cloudy days ahead? You will have nearly nothing from your photovoltaic because it's so cloudy. In this case, we can produce more heat on the last sunny day, and on all the cloudy days, on the water-to-water heat pump takes out heat from the low temperature storage and put it in the floor heating and so on. And we need in these days much less electric power because we don't need to take heat energy out of the air. Same applies when the weather forecast tells, oh, very cold weather ahead. Then we try all the day to use our air heat pumps to bring the low temperature heat storage to a higher temperature. And all the day when it's very cold, we don't use the air heat pump. We skip these days. And so we can maybe have with these systems a higher yearly coefficient of power than a usually water-to-water heat pump. This we want to achieve with this patent, that we can use air heat pumps really everywhere, because the big disadvantages of the air heat pump are with the low temperature heat storage away. Another problem is soil sealing. In the German area, this is called a very big problem. Soil sealing. You should not make a house. Soil sealing. And we have an argument against soil sealing arguments. Let's assume it's Monday and the weather forecast tells extreme rain expected for Thursday. What to do now? We put 20 cubic meters of the 40 cubic meter low temperature heat storage away. We make room for much rainwater. On Wednesday, we are well prepared for the extreme rain. And on Thursday, the extreme rain comes, and we show that we have negative soil sealing. The built over area absorbs more water than a meadow. And we have destroyed this argument against making a new house. We have negative soil sealing. You can go away with your soil sealing arguments. Now, domestic hot water. There are several different methods to prepare domestic hot water. Most common is the boiler. There is water from the water pipe. This water is warmed up to 62 degrees Celsius. Why 62? Oh, this is the Legionella killing temperature. Hot water systems should be free from Legionella because it's a dangerous bacteria. And so we have to kill the Legionella with 62 degrees Celsius. And so with the heat pump, we have only a very low efficiency. The COP is only 2.23. And when we assume for a typical shower, 3 kilowatt hours of heat is necessary, we use for this 1,343 watt hours of electrical power. The advantage of the boiler system is that I can use the water up to the last water droplet inside. The water goes away and away to the shower, and suddenly there's no water there. The next system is the fresh water station. Here, the water from the water pipe is warmed up by a plate heat exchanger to the temperature we need for a shower. And we need right in the middle up a sensor. the sensor tells, oh, there's a water flow. And when the water is flowing, there's a water pump, and this water pump puts water from the heat storage to the other side of the plate heat exchanger. So we can use a lower temperature because we don't need to kill Legionella, because the water from the water pipe is in seconds heated up to the temperature we wish. But the disadvantage is we take out heat from the heat storage, and when we start with 52 degrees, soon comes the point where the heat storage has only 40 degrees, 38, 36, the water feels uncomfortable, cold for a shower. This is a disadvantage of this system. To overcome all these problems with domestic hot water, we applied for another patent. Here we have 3 plate heat exchangers, 3 water pumps, and 3 heat pumps, and a very small but very high isolated water storage. What we do with all this, we heat the water in steps upwards. This means the water comes with 6 degrees Celsius out of the water pipe. 6 degrees I measured myself in February this year at home, and the first heat pump heats this up by the plate heat exchangers to 20 degrees Celsius. And because we have only to 20 degrees Celsius, we have a very high COP of 6.51. And the next heat pump heats up the water from 20 to 30 degrees. And again, because we heat up only to 30 degrees, we have also here a very good COP of 4.33. And only in the last step, we heat up to 40 degrees Celsius. And here we have the usual low coefficient of power, 3.3, but we use this only for 30% of the warm-up work. Most of the work to warm up the water is done by much higher COP, and so we use here only 661 watt-hours of electric power to generate these 3 kilowatt-hours of heat for a typical shower. And this is only one part of the story. We have not mentioned here storage losses. Here we have only a very small between storage. This is used not to start up the whole big system when somebody wants only to wash hands, 30 seconds and 3 liters per minute, and we want not to start up the whole system for such small applications, but for making a shower we can have a very high efficiency, and because we have not big storage devices, this counts also, so maybe we have far beyond only half of the power usage. Maybe this is the savings of power is much bigger. But what happens when people say, oh, I need really hot water. I like it hot. One vendor of heat systems for houses made 2003 an experiment with it. He delivered a domestic hot water system only for 42 degrees Celsius. He know, as I know, the Carnot process, the COP, and all the problems at temperature differences, and so he thought he can save much electric power when in all the village is only 42 degrees Celsius for the domestic hot water. No man complained. No young woman complained. only woman older than 30 complained, "Oh, I want make my dishes clean and the water is not hot enough for doing this. I need really hot water." And so he had to finish this experiment and put all the heating systems to a much higher temperature to fulfill the demand of this woman who want really hot water for dishwashing. And sure, there is a third patent we applied for to deal exactly with this problem. This was another video from Roland Mösel, founder of Planetary Engineering Group Earth, and as always, like, comment, subscribe, and hit the bell to be notified when I make my next video about great technical developments.